Now, in a normal deployment scenario, how does it look? Well, basically, you've got your radio base station with basically your G node B and E node B both. Because we're running this in non-standalone, your E node B and G node B is co-located on the same site. So when your user is connected to the site, it has what we call an ENDC, or Enhanced Dual Connectivity Connection to the site. So it's basically anchoring off the LTE, but it's using the NR for the throughput. So we'll have a anchor layer of LTE and using NR. So in this scenario, the DSS is operating in low band with NR and LTE sharing spectrum. So this could be a DSS phone with the right. We'll talk about some of the requirements for DSS phones, like what we need. For you can't just buy a phone off the shelf, and it doesn't just support DSS by default. So it has to be a specific kind of firmware. But anyways, we've got spectrum sharing happening in this sort of NSA scenario. We spoke of some of the operator benefits, so it's a bit deeper. It allows for instantaneous sharing between NR and LTE based on real-time traffic. So your traffic load conditions are always changing in the network. You don't have static conditions, right? You know, people are waking up in the morning. Your traffic volume is increasing when people are sleeping. That is during non-peak hours. Your traffic is dropping. So you want to be able to dynamically share the spectrum so to accommodate for these changing traffic load conditions. This is something that DSS allows for because it is a dynamic spectrum sharing feature and not a static spectrum sharing feature. So this is some of the advantage we are using. And also DSS has a scheduling algorithm with resource allocation. We'll talk a bit more about the interface later on. So the scheduling algorithm with resource allocation, which can be used in both in frequency and time domain. When used in this fashion, it can dynamically share spectrum between LTE and NR. Also, GBI versus non-GBI. So GBI are your guaranteed bitrate services. So especially, you know, if you look at your IMS or your emergency VoLTE services, they have higher priority than non-GBI, like packet data. So we want to be able to do this sort of QoS prioritization or priority scheduling between GBI and non-GBI traffic. So DSS accommodates for that. So you know, for your emergency voice, you definitely need your GBI services running. Also enables coexistence of non-standalone, standalone, and LTEs in a shared bandwidth channel. So obviously the bandwidth channel is the same. It's the same FTD carrier that we're using. So when LTE and NR is sharing that, we call it a shared carrier. So then basically in various deployment scenarios, non-standalone, standalone, the LTEs are working on a shared bandwidth channel. We spoke about the nationwide coverage. We spoke about the high band spectrum being used for increased coverage and capacity. So that's our carrier aggregation scenario. And also it allows for a faster migration to standalone architecture. So if we cover these deployment options, so we've got a couple of options here. First one being your spectrum refarming. So this is something that operators were doing before, right? So this, we're moving away from that model. So we're moving away towards a soft refarming model because in order to do spectrum refarming, you're actually turning off 4G to enable 5G. So you're actually completely changing the spectrum usage to 5G. So effectively, you've lost 4G. So all that bandwidth you had, all the spectrum you purchased for 4G that operators purchased, they cannot use it for 4G anymore because they need to give it 5G because so that's what spectrum, conventional spectrum refarming is all about, and that's something we don't want because this will ultimately impact your LTE capacity because now you have one less band that you can use for 4G because now it's being used for 5G. So the option 2 is your static spectrum sharing. So it's like you're allocating 10 megahertz for LTE, 10 megahertz for NR, and then that's your static spectrum, and that's all that's going to be used. Doesn't matter what the traffic conditions are. That's what it's being allocated. So that would churn the bandwidth a lot. And traffic modeling might be done, and it might be a bad idea, especially in your high capacity traffic scenarios, where you need more NR bandwidth, but you don't have it because you only have a fixed allocation for it. So then it requires a lot of planning and dimensioning by the RF planning engineers to make sure that they're doing this in a correct way. But with a dynamic spectrum sharing, so what we also call is option 3, soft refarming, that changes the whole picture, because now we're actually using the instantaneous traffic load conditions of the network to dynamically allocate spectrum to LTE and NR. So this is where the benefit comes. And this tends to be most suitable for the introduction of 5G into an existing LTE FDD carrier. So if your FDD carrier is, say, 2100 megahertz, you can run 2100 megahertz for both LTE and NR with dynamic spectrum sharing. So this is us comparing the spectrum refarming versus your dynamic. So this is your classical refarming. You're basically, as an operator, you're starting to introduce 5G. Your 5G footprint grows, and then eventually you need to start phasing out your 4G, because you're doing your classic spectrum refarming. Therefore, your 4G bands tend to be underutilized. But what the advantage of DSS is, you introduce 5G, your 5G traffic volume grows, and your site density grows, and all good and well. But you don't need to phase out your 4G completely, because your devices can use both 4G and 5G in DSS mode. So if we just look at this a little bit more deeper, most common deployment scenarios of static spectrum sharing is the reduction of spectrum for LTE, making it difficult to meet traffic demands. So this is where the bottleneck lies. You can't meet your traffic demands with static spectrum sharing at times. Less bandwidth available for each RAT, right? Because you're only giving 10 megahertz to, say, LTE and 10 to NR, and that might not be enough bandwidth. And spectrum sharing will retain full bandwidth and peak rates for each RAT, which that's the advantage of DSS. And the spectrum capacity is dynamically assigned to match current traffic and conditions. So that's the key benefit, I can say, for DSS is you're matching your current traffic conditions, which always keep changing. If you're doing some capacity traffic modeling, you can find out that the network capacity conditions are always changing in a live network. Common resource grid for LTE and NR. So we'll talk about the area interface shortly, about how we have a common resource grid that we share between LTE and NR in order for DSS to work. That's the advantage of using the area interface in this way. And our PDS-CH mapping, PDS-CH, your physical downlink shared channel to avoid collisions. Collision avoidance for LTE and NR, PUS-CH, which is your uplink. And also your downlink scheduling coordination between LTE and NR transmissions to avoid collisions. So why we're doing this, it's basically we have a scheduler in the MAC layer. So obviously in 5G, we've got the physical layer and MAC layer, PDCP, RRC, etc. There's multiple layers. In the MAC layer, that's where this physical resource block allocation is happening. And it happens adaptively so as to avoid collisions. Because remember, we're using the same carrier. So it's a shared carrier, same band. You would think there's going to be interference, but the intelligence of this air interface is ensuring that interference doesn't happen. Because we're doing stuff like rate matching to ensure that doesn't happen. So we'll talk about that more shortly. So now moving on to the area interface concept. So this gets really technical. This is where the magic is happening in terms of the scheduling and spectrum resources. So the fundamental challenge is that LTE and NR share the same resources, right? So the resource block you can see as here, this could be a common resource block between LTE and NR. So what we want to ensure is that the signals do not collide. So in order to do that, we use various techniques. So we do various things with the air interface to avoid that. Spectrum sharing requires tools and configuration to avoid collisions, and also common cell-specific reference signals rate matched, so NR signals can occupy the same resource grid for better spectrum efficiency. So it's this rate matching that's allowing LTE and NR signals to be used on the same physical resource grid, because this resource grid is nothing but it's carrying what we call PRBs. These are your physical resource blocks, you know, for OFDM with some sort of subcarrier spacing. And ultimately, these resource blocks are your radio resources, right? Which is effectively, transmitting data. So this becomes, you know, a really important intelligent way of managing this the spectrum resources. LTE control channels are adjusted so that NR control channels can be transmitted in the same resource grid. MBSN, which is multi-broadcast single frequency network, is used in LTE for multi-point transmission, where specific subframes in an LTE frame reserve the last 12 OFDM symbols to be free from the other LTE channel transmission. So you need to change the MBSN frame size in order to use LTE and NR in this fashion. And the key is to avoid collisions, because we don't want the radio frames to have collisions between them. So we do this these intelligent air interface techniques like MBSN or rate matching, CRS rate matching to make sure that the LTE channel does not collide with the NR channel. No collisions occur between NR and LTE control channels. So using LTE cell-specific reference signal rate matching in NSA that is non-standalone and standalone, we have basically an intelligent scheduler. What that scheduler is doing is it's assigning resources to LTE and NR. So it's got a scheduling algorithm built in to that scheduler, which is sort of allowing you to adaptively schedule radio resources. We also have to maintain inter-RAT fairness. Inter-RAT is basically, RAT is radio access technology. So the RATs are 4G and 5G. So to maintain inter-RAT or 4G, 5G fairness, we're comparing resource block priorities to perform resource allocation. So then we are assigning priorities to 4G and 5G in an intelligent way to perform resource allocation. LTE PDC-CH occupies 1 to 3 symbols based on cell load, with the first 2 symbols used for LTE PDC-CH and NR-UE occupies the 3rd symbol. So that's normally how these symbols are used. The first 2 symbols are used for LTE PDC-CH, and the 3rd one is used for the NR-UE. And we already covered this point that based on the real-time traffic, the resource allocation takes place. Physical resource block allocation. So we spoke about the bandwidths, 10, 15, or 20 megahertz channels. We're basically sharing those as these are the bands that are supported for DSS. So then we have these bandwidth channels that we need to work with. So spectrum allocation between NR and LTE is handled in both frequency and time domain. So this is crucial. So not only is the spectrum allocation done in frequency domain, but it's also in time domain. And in frequency domain, the PRB allocation varies between 3 levels. So level 1 is your 100% PRB is used for NR. So all your physical resource blocks are used for NR. Your option level 2 is when 50% is used for PRBs are used for LTE and 50% for NR. And then your last one where 100% of your PRBs are used for LTE. So this selection of which option to go with is based on the UE carrying data. So it's based on active UEs basically in how you're going to do your PRB allocation. So again, it comes back to your traffic load and your current traffic conditions. Your PRB is split between NR and LTE, evaluated every TTI. So TTI is your transmission time interval. So how often the transmissions are happening for LTE and NR is governed by the TTI granularity. So again, coming back to the scheduler, so this is a LTE MAC level scheduler. What it's doing, it's loading resources to NR. So this scheduler originally is in the LTE, and it's basically your MAC scheduler. Your LTE scheduler is the master scheduler with spectrum allocation based on the LTE scheduler. And there's a lot of overhead between LTE and NR spectrum, right? So because we've got spectrum overlap, we want the scheduler to work intelligently. We want it to assign resources in a way when it can share those resources in between LTE and NR. So mini-slot operation eliminates the use of symbols. That contains LTE common reference signals and schedules only free ones for NR transmission. And finally, NR uses scheduled on top of LTE carriers while avoiding channels used by LTE. So again, the MAC layer scheduler is basically the most intelligent scheduler there is that allows for DSS to work and share radio resources. If this was, if the scheduler is not designed in this way, we can never ever intelligently use the air interface like we are. Also, NR avoids symbols used in LTE for cell-specific symbols, right? So we're trying to avoid the symbols of LTE. So we have a clear definition. What are the NR symbols and what are the LTE symbols? Cell-specific symbols, that is. The LTE and NR cells use the same PRBs, right? So we spoke about the resource grid. We said that there's a common resource grid that we're using, and TTI is obviously transmitted through a shared carrier as well. Which is your, say, in low band, 2100 megahertz could be a shared carrier. Placement of reference symbols and control channels in the shared carrier is orchestrated by a combined scheduler for both routes. Now, the scheduler determines how to split the resources. It weighs the type of traffic and considers higher priority traffic first. So we spoke about GBR, non-GBR. So for example, your GBR services are considered higher priority, and it's going to have a weighting scheme. So it's going to give a higher weight to high priority traffic, just like how we do in QoS. So it would have a way of weighing the traffic in that way. Also evaluating traffic load of the connected LTE and NR UEs during each transmission time interval. So it needs a way of doing this traffic modeling and being able to weigh the traffic load currently in the network. And obviously, we need to be able to calculate the number of PRBs needed for the UEs of each radio access technology and allocate resources with the highest granularity in the frequency domain. These are some of the things we need in the scheduler, DSS. Some more points here. Legacy UEs connecting to LTE bands do not realize NR UEs have the functionality to share spectrum. There's no impact on legacy LTE UEs. So basically, if you've got a 4G legacy UE, you can still connect to a non-DSS carrier. So you can still attach to the network. So it doesn't mean if you have DSS enabled on the site, your legacy UEs are not going to work. It's just that only your DSS UEs will be able to use this feature. We're going to talk about some of the UE requirements soon on what those DSS UEs need. So certain chipset vendors are preparing for the DSS solution. So your Samsungs, your Apples, they're doing a lot of research on DSS, and obviously the RAN vendors like Ericsson, Nokia, or Huawei are leading the way in terms of the actual network side and the radio technology. But soon to follow are the chipset vendors. They are still behind in terms of features that are being rolled out, or 5G features that are being rolled out in the network. And sometimes features can be enabled from the radio end, but the UEs can't really use it because chipset vendors are a little bit behind. But chipset vendors are very quickly enabling DSS UEs, so that's good news. So we'll start seeing more of these commercially. So the NR UEs require functionality called common cell-specific reference signal puncturing to support DSS. This is one of the DSS UE requirements. And some of the others include the UE needs to support rate matching. It needs to support DMRS symbol locations that do not collide. So it needs that collision avoidance at the MAC layer. If it didn't do that, then DSS just won't work because you'll have collisions between LTE and NR transmissions. Supporting pattern matching to avoid collisions with LTE control channels. And also, if the UE does not support above, no problem. It does not need to attach to the DSS cell. So if there's a neighboring site, or even the site that's serving you currently, and the site is, has DSS enabled in the baseband, so let's say in the 4G baseband, then your UEs can still anchor off that site. It does not mean it can't establish a connection. It can still work regardless. So these are your legacy LTE UEs, that is. If non-compatible UE does not attach to the DSS channel, it will attach to a non-DSS channel. So that's the point, shown by another NR carrier. So you might have NR 3500 megahertz carrier, and you can simply attach the 5G using that carrier. You don't necessarily need DSS carrier. So a lot of the requirements are mentioned in release 15, including uplink shifting, CRS rate matching, general rate matching to map LTE sync and PBCH. So basically, this is where the chipset vendors are coming in and enabling some of these capabilities and functionality, so they can start rolling it out with the right kind of UEs. Now, let's speak from an RF planning and design engineer. So if you need to deploy DSS in your network, what does the planning engineer need to consider? Well, you need to consider what are the FDD carrier bands that we can use, because every operator would have purchased different spectrum. So we need to know what spectrum can we use, which one is the most highly deployed, which one has the highest coverage. And so in Australia, for example, 2100 megahertz is used by Optus as the shared carrier, as they have the biggest footprint of this low band carrier. So your planning engineer would consider that, and it was an anchoring decision to use that carrier for DSS. And how that decision is made is, you're trying to maximize your coverage and capacity. So we want to choose a shared carrier which can give you the maximum coverage capacity. So that's why it's important to understand what bands are available by the operator. DSS shared carrier selected from the available spectrum, and then your network planning ensures good selection of DSS shared carrier and anchor carrier for the operator network. So you still need an anchor carrier. For example, if for this not standalone architecture, the UE still needs a 4G anchor to connect to 5G. So to say connect to 2100 megahertz, band 1. So this is band 1 here. Connect to this band, it might use a different anchor carrier, say band 7. It might use band 7 as an anchor carrier still. So when I mentioned ENDC, that's when you're using a different anchor to your shared carrier. Only when we have standalone does it not need an anchor. So for all non-standalone deployments, we need an anchor carrier as well. So some of the anchor carrier guidelines are the operator needs to suggest an LTE band for NR refarming with dynamic spectrum sharing based on the below suggestion. Choosing an LTE band with narrowband IoT, one carrier shared by LTE and NR. LTE anchor carrier must be in a different band, so you can't obviously use the same band for it. And then you also need to be able to prioritize the bands you have as options, and also choosing a band with reasonable radio penetration. Because you want this high coverage on low band, we want to make sure the radio penetration is quite good. For selecting the anchor carrier for NR band, check the possible LTE anchor bands specified in 3GPP for candidate NR bands, and ensure that that combination works. So you need a good anchor layering strategy by your operator in order for you to roll out DSS. Okay, so thank you so much for listening to my presentation. I'll just conclude with the final conclusion. Some of the key points we're going to draw out is how the spectrum sharing landscape helps in understanding deployment. So coming back to the learning outcomes, which feed into the conclusion. Second point is the DSS is the first step towards your nationwide coverage. DSS is deployed in low band. We spoke about that. We spoke about some of the advantages it has. There was static spectrum sharing. We covered scheduling, the MAC LTE scheduler, and how scheduling is so important for sharing radio resources. And we also touched on the UE compatibility and also network planning and design considerations for ESS rollout.